I apologize again for deleting the lecture from this morning. Actually, I didn't delete the lecture from this morning. I just completely forgot to hit record. So I'll go back over the stuff that I talked about today in class. So we talked about row space, column space, and null space before break. So just as a reminder, the row space of a matrix is the span of the rows of A. Since each of your rows has the same number of components as there are columns in the matrix, this is going to be a subspace of Rn. Just as a reminder here, we'll have A is an m by n matrix. All right. Your column space is the span of all the columns. So your columns go down your rows, of course, of the matrix. As we're going down the rows here, we see that we will go down m components, if you will. And so we can think of each of those vectors as a vector in Rm. So the column space is a subspace of Rm. The null space, of course, is the set of solutions of the system AX equals 0. If A is an m by n matrix, X has to be an n by 1 matrix to make this multiplication work. So any solution to this has to be an n by 1 matrix, or we can think of that as a vector in Rn. So the null space is a subspace of Rn. So just to recap, your row space is a subspace of Rn. Your null space is also a subspace of Rn. Your column space is a subspace of Rm, and we'll come back to these concepts later on in this video as well as in a next chapter. All right. To see, we talked about before the test as well, that the elementary row operations don't change the null space at all, and here's why. It better not, right? Or what we talked about how to solve these kinds of things would be wrong from the beginning of the semester. So why is that true? Well, I can think of, when we do the reduced row echelon form of A, I can think of doing that as a sequence of elementary row operations, or as a multiplication by a sequence of elementary matrices. When I do that enough times with my elementary matrices, I get the reduced row echelon form of A, and that's how we read off the solutions. Each of these is invertible, so I can also go backward to get to A. So whatever's a solution here is a solution here, and vice versa. If it makes it work in this equation, it makes it work in this equation. Likewise, if it makes it work in this equation, it makes it work in this equation. So that's why we see that the elementary row operations have no effect on the null space. It also makes sense that elementary row operations have no effect on the, that was on the null space, on the row space, because elementary row operations are linear combinations of the rows. So all we're doing is saying, okay, if we have a linear combination of these rows, then we could have a linear combination of these rows, and I get the same thing, because these rows are linear combinations of these rows. Okay? So that's why the elementary row operations don't change the row space. However, they do change the column space, and that one's pretty easy to see. When we do the reduced row echelon form for this particular matrix, I get zeros in the lower row here, the second row here. That means if I do linear combinations of the columns, looking at the span of the columns here, the only thing I ever get here is 0, no matter what. No matter what I try to do for a linear combination, this linear combination of these two vectors is always going to have a 0 in the second component. However, over here it's pretty clear to see that I can get any even number I want as the second component. And in fact, I notice that this one is a scalar multiple of this one, so really I can use this first column to generate the entire column space. But notice it has a 2 in the second component, and this one can never have a 2 in the second component. So I don't get the same space at all. Okay, so it changes when we row reduce. Now our challenge in these problems is going to be to find bases of the row space, the column space, the null space, and all that jazz. So in order to be able to do that, I need to talk about bases. Well, we've already talked about how to do bases for null space. So if this is my example here, with this matrix here, and again, I apologize, I didn't mean to have that extra column on there when I made this particular file. I see that we have free variables here in column 2, 5, and 6. So we know already how to write the basis for the column space. We know that I can write anything as r times a negative 3, 1, 0, 0, 0, 0, and s times, so the s is here. The first one's going to be negative 1, 0, 0, oops, yep, this is 0. Sorry about that. Just trying to erase, and it's not erasing. So apparently I can't erase like I do with the other one. Erase. Sorry. Okay. All right. So this one, oh, I don't think I've written this right. Let me go back and fix this. All right. So if I go back and fix this, it says that x1 is equal to negative 3r plus minus s. Okay, really does not want me to erase it that way. Minus s plus 2t. This is x3. x3 is s minus t. And x4 is negative 4s minus 2t. So then I should be able to write my basis now as negative 3, 1, 0, 0, 0, 0. That's the r. The s is going to be negative 1, 0, 1, negative 4, 1, 0. And the t is going to be 2, 0, negative 1, negative 2, 0, 1. And so these three vectors will form our basis for the null space. As for the basis for the row, and we've already done things like this before. Basis for the row space. Well, we said that this is the reduced row echelon form of this matrix, and this did not change the row space of the matrix. So I look at these three rows that are left, and I notice that they're linearly independent. There's no way to get this one up here in this component from these two zeros. There's no way to get this one from these two zeros, and there's no way to get this one from these two zeros. So these rows are definitely linearly independent, without a question. Okay. So, a basis for the row space then, and I'm going to write them as tuples. We will have 1, 3, 0, 0, 1, negative 2, 0, 0, 1, negative 0, negative 1, 1, and 0, 0, 0, 1, 4, 2. Notice I did not go back and grab original rows to write down the basis. I had to grab the rows in the reduced row echelon form. The reason behind that is the following. When we do the reduced row echelon form, I don't know which of these rows actually correspond to the rows over in the reduced row echelon form, because we have row swapping that also goes on as an elementary row operation. So it's entirely possible that we would have gotten a row of zeros somewhere up here that got swapped down to the bottom. So in that case, I just don't know which of these pair with which of these, so I can't use the originals. I have to use the ones that are in the reduced row echelon form in this case. Okay, so finally then for the basis for the column space, we've done things like this already before, we just haven't called it this. We do know that these three columns correspond to the three linearly independent columns back in the original. As we've done this. That's how we were checking to reduce things to a basis, right? We put them in columns in a matrix, row reduce, and go back and pick the columns that corresponded to the pivots in the reduced row echelon form. So those particular columns will be the ones that are in the basis for the column space. I'm just going to write this down here in the lower right corner. The basis for your column space is going to be, I'll write them as columns, but really, again, we can think of these as vectors in Rm. So in this case, R4. So I could write them horizontally as well. and it won't matter because it really doesn't matter the orientation that we write them in. All right, so that's how we find basis for row space and basis for column space and basis for null space. Now, in some of the problems, you might be asked to find a basis for the row space that involves the original rows of A, and that relates to this idea of being able to do the transpose. So certainly, it's pretty clear to see that the row space of A has to be the same as the column space of A transpose, and vice versa. So if we want to find a basis for the row space that involves original rows of A, what I can do is, well, taking the transpose changes rows to columns. So I can find, take the transpose of the matrix, put it in reduced row echelon form, and then go back and pick out the columns that have pivots of the transpose, and that'll correspond to the rows that'll have pivots, and I can use that for my basis. So let's see if we can do this by example here. I don't have the calculator on this particular computer, so I can't do this by example with the computer. We'll do it by example using a different program here. Bear with me for a second as I get this other package opened. All right, so my apologies. All right, here we go. So, first thing I want to do is get a matrix in here that you can actually see. All right. There we go. All right. So let's see here if we can get this to row reduce. All right, so I have to remember what the actual matrix was. So let's do that here. Trying to get to another file open here so that I can see it and not have to switch back and forth between screens. So again, just bear with me for just a second. I know this isn't going to be the highest quality video, but that happens sometimes. All right, here we go. Maybe here we go. First one was, there we go, finally. All right, so the matrix was 3, 9, 2, -7, -27, -18, -9, -27, 4, -6, -37, 10, 2, 6, -1. This is why I usually have this stuff in here already, but I forgot that I didn't have the emulator on this computer. The other computer was acting wonky. I had to buy a new one, so this is why I'm doing it this way. All right, so let's just check our reduced row echelon form here, and we do get the same thing as what we had before. All right, so now instead, let's take the transpose. I can see where it says transpose. There it is. There's our transpose. So now I want to do the reduced row echelon form. And now I see that pivots, when I do the reduced row echelon form, correspond to the first 3 columns. So when I go back to my basis for my row space, I really could have picked out the first 3 rows and gave me a basis for the row space that involves the original rows of A rather than the rows that were in the reduced row echelon form. So switching back over now to the right up, we know that the basis for the row of A involving only rows of A will be the first three rows, which is the 3, 9, 2, -7, -27, -18, the -9, -27, 4, -6, -37, 10, and the 2, 6, -1, 1, 7, -3. All right, so another thing that we notice here is that with these transpose things, that of course when I do pivots, well, we have the same number of pivots in rows and columns no matter what, right? Because we get a pivot in a row, then we move over to it in the next column that we can to get another pivot and move over. We always have the same number of pivots, whether we count by pivots by column or pivots by row. So that also tells us that the dimension of the row space of actually the dimension of all of these spaces, dimension of row space, dimension of the column space, dimension of the row space of A transpose, and the dimension of the column space of A transpose are all the same. And the common number that they're all equal to is the rank of the matrix, because remember again, the rank is the number of pivots. So all of those things are all equal to each other. By columns of the matrix, we know that either a column has a pivot in it or it doesn't. Those are the only two choices. The number of pivots is the rank. The number of free variables is the nullity. And again, either a column has a pivot, so it adds to the rank, or it has a free variable, so it adds to the nullity. If I added those two quantities together, I get n, the number of columns of A. And then I already mentioned up here that our dimension of our row space of A and the dimension of the column space are both n. If we have that, if n's the number of, I'm sorry, that's not n, it's the rank. Still getting used to the new setup. Sorry, my apologies. So those are both equal to the rank, and so that the dimension of the null space, let's say we call this R, then the dimension of the null space of A will be the number of columns minus the R. Okay, so let's talk a little bit about the rank and the consistency. All right, so let's think about what happens if I take a matrix A and I row reduce it. So I augment by the B and row reduce it like I'm trying to solve the system AX equals B. Well, if it's inconsistent, then I know that when I row reduce, I get a pivot, I get stuff here, right? I get a pivot, but then eventually, if it's inconsistent, I have to have a row of zeros and a 1 in the right-hand column there. That's what it means to be inconsistent, right? I get a system that says when I do the reduced row echelon form, I end up with a 0 equals a 1. That's what inconsistent is going to tell me. Well, notice what happens then. These pivots would give me the rank of A. This would add 1 to the rank of A if it's inconsistent. So what we can say is that the system AX equals B is consistent. It has a solution if and only if the rank of the matrix A augmented by B is the same as the rank of the original matrix. If augmenting by B makes the rank go up, then you get a row of zeros equals a 1. which says that the system was inconsistent. That's all that particular theorem says. So what this tells us is that, okay, so if A is m by n, and I look at the rank, we've answered this question before, but let's go ahead and do the same idea here. In order for span to happen, I need to have a pivot in every row. So we can say that the row space of A spans, where were those? Rn. Spans all of Rn, if and only if. What has to happen? Well, we know that when we row reduce, we have to get a pivot in every row, so that means that the rank of A has to be m. We have to be able to get a pivot in every row to be able to span all of Rn. I think I just said that backward. Let me think about that for just a second. Well, the rank can't get any higher. That's not what I meant. Let's go back to this again. Sorry. Let's talk. I don't want to talk about the row. I want to talk about the column. I want to know if the column space spans or not. Not the row space. My apologies. I said that backwards. I want to know if the column space spans or not. And this spans Rm if and only if the rank is m, meaning that we have to have a pivot in every row. We better have a pivot in every row if it's going to span. If we make the linear combination, think about what this means. If I make a linear combination of the columns, well, I better be able to get, say, like if you had a R4 here, I better be able to get these types of vectors to be able to span, right? I need to get those vectors, those pivots in every row. So the column space is going to span all of Rm, that's where it lives, if and only if the rank is m, because that gives us a pivot in every row. And we've already talked about that idea. For linearly independent, well, we've already talked about this before as well. The column space, let's write it this way instead. Let's write it as the columns of A are linearly independent if and only if. What has to happen? Well, we know that the columns are linearly independent if and only if there's a pivot in every column. Well, there's n columns, so the rank of A better be n. Okay, so the column space will span, or it equals all of Rm if the rank is m. That means we get a pivot in every row. Their columns are linearly independent. That means we get a pivot in every column, which means the rank has to be n along the columns. Now, if it has to do both at the same time, this has to equal the number of rows, this has to equal the number of columns. So if it's going to be linearly independent and span, then it's going to have to be square, and you end up with the rank being the n, where the size of the matrix is n by n. So this is where we get the return of our mega theorem. So remember, the first condition here was that A is invertible. And I think we are down to H, I think is the next one. So again, what we just talked about in the previous thing was that we figure out where there are pivots. Okay, so if it's n by n, if we get a pivot in every column, then the columns are linearly independent. If we get a pivot in every row, the rows will be linearly independent, and in the same way with the span. So this says that the columns span Rn. I says the rows span Rn. Then we have the equivalent condition for linearly independent. Oh, but this is what it does, yeah. This says that the rows are linearly independent. And if they're both, then that means that the columns form a basis for Rn in both cases. Now again, the whole reason for why this is true is because it goes back to the reduced row echelon form of A is the identity if it's invertible. Well, if the columns span Rn, then you have to get a pivot in every row to be able to do that. And then likewise for the rows, same thing with the columns. The rows end up being with doing it with the transpose. You get a column span Rn, you row reduce, you get a pivot in every column, which means it also has a pivot in every row. So it looks like the identity matrix. The rows span, well, take the transpose, row reduce, you get a pivot in every column. So the columns of A transpose span, so the rows span. Same idea for linearly independent, same idea for a basis. It's the same idea we talked about taking the vectors, putting in columns in the matrix, and row reducing and looking for the pivots. This is all these six are saying. The last two, counting, well, if there's a pivot in every column, then that means the rank of A is n, the same as the n by n. And if the rank is n, there are no free variables in the reduced row echelon form, so the nullity is 0. So we get these 8 additional conditions for a matrix being invertible, but again, they all boil down to the fact that the reduced row echelon form of an invertible matrix is the identity matrix. So that's all this is being able to row reduce and seeing that. All right, so that takes care of the stuff with row space, column space, and null space. I still need to talk about a little bit of the beginning that we talked about with inner product spaces, and we're going to continue this on Wednesday. So give me a second while I open that file. All right, so let's scroll back up to the top here. Maybe. There we go. So basically, I just talked about why we care about doing inner products here. Well, the whole point of products is to be able to do things like take a length of a vector. So we'll be able to assign lengths to vectors. Now, if we have a vector in Rn, we can absolutely do that. If you've got, say, an x equal to x1, x2, out to xn, then I know that the length, the magnitude, the norm of x is just the square root of x1 squared plus x2 squared out to xn squared. And if you've seen dot products before, this is just the square root of the vector dotted with itself. Dot product, inner product are the same thing as far as we're talking about with Rn. So that dot, when we take the vector and dot it with itself, it allows us to do this computation and be able to assign a magnitude to a particular vector. Now again, we do this already in Rn, but we don't do it in things like polynomial spaces or matrix spaces or function spaces. And sometimes it's nice to be able to do those things. Say you want to be able to do a polynomial regression or a what's referred to as a Fourier series to approximate a periodic function. These require ways to measure lengths. Okay, if you don't have what's referred to as an inner product on those particular vectors, you can't measure length, which makes those kind of regression types of things or approximation type things really, really, really difficult. So, assigning lengths are something that we want to do. Assigning distances between vectors. This goes to the least squares idea. if you have another vector y, which is y1 out to yn, then the distance between x and y is the square root of x1 minus y1 squared all the way out to xn minus yn squared. That's the distance between those two things. And then the last thing is to be able to assign an angle between two vectors. Now again, these ideas, when we don't have a dot product, are really, really hard to do. We've seen it in Rn, but we have a dot product, an inner product assigned in Rn. So what we're going to be concentrating about is what properties of that dot product, inner product in Rn, are necessary to talk about an arbitrary inner product, and then how do we define things like length and distance and angle. So that's where we'll pick it up on Wednesday.